Deep water environments like Seattle's Lake Washington and Norway's Bjørnafjorden represent a severe constraint for civil infrastructure. In Washington, a 65-meter water column rests on top of a 60-meter layer of soft mud. Those benthic measurements make sinking traditional bedrock piers physically impossible. The engineering workaround is to replace bedrock foundations entirely. Instead, the spans are supported by massive, watertight concrete pontoons, tethered in place by sturdy steel cables. This design introduces a primary vulnerability. It exposes the structure directly to environmental loads. Low-frequency environmental forces like wind, waves, and ocean currents constantly interact with the pontoons, inducing continuous structural sway and vertical heave. Disconnecting a bridge from solid bedrock transforms it from a static roadway into a constantly moving, dynamic multi-body system. The Norwegian Public Roads Administration sought an analysis of exactly how these massive structural bridge motions transfer into a traversing passenger bus. Mechanically, these forces travel upward from the bridge pontoons, through the roadway deck, and directly into the vehicle's suspension system. From there, the mechanical suspension vibrations propagate upward into the human biomechanics of the driver and the passengers. Engineers at Chalmers University identified a core optimization paradox regarding the vehicle's speed on a floating bridge. First, higher traversing speeds degrade physical passenger ride comfort. Second, reducing the vehicle's speed actively increases passenger motion sickness. Solving this tension requires a rigorous mathematical framework capable of balancing two entirely different human physiological responses against raw structural data. To predict human responses to forces that haven't been recorded yet, engineers constructed a 13-degree of freedom mechanical model. The model defines the bus body mathematically as a single sprung mass, subject to vertical, pitch, and roll accelerations induced by the bridge. Inside the vehicle, the layout treats the driver and three passengers as four distinct point masses. These point masses are mechanically connected to the floor using specific spring stiffness and damping coefficients to represent the seats. The model highlights geometric variables S1 through S8, representing the exact longitudinal and lateral distances from the center of gravity to each seat. The differential equation of motion for a specific passenger's vertical acceleration is a function of both the suspension inputs and these geometric distances. Any pitch and roll angular accelerations originating from the bridge are multiplied by that distance from the center of gravity. As a result, the further a passenger is seated from the center of gravity, the greater the lateral and vertical displacement applied to their body. A passenger's geometric coordinate inside the vehicle dictates the raw mechanical acceleration applied to their body. Raw mechanical acceleration data does not equal human discomfort. The human body is an anisotropic receiver. It possesses highly specific sensitivities to different vibrational frequencies. Engineers quantify this sensitivity using ISO 2631-1 frequency weighting filters. This chart graphs the frequency weightings. The WK and WD filters exhibit specific arc shapes with broad active ranges. The 0.5 to 80 Hz range isolated by these filters is used to evaluate physical ride comfort, measuring high-frequency impacts to the feet, back, and buttocks. In contrast, the WF filter has an entirely distinct, sharply peaked shape on the graph. The WFRIF filter strictly predicts motion sickness, and it only registers in the ultra-low frequency range of 0.1 to 0.5 Hz. Filtering raw acceleration data through these distinct mathematical curves is the only way to separate the mechanical jarring of the suspension from the physiological trigger of nausea. With the ISO frequency filters applied, the mechanics behind the traversal paradox become clear. The first metric, physical ride discomfort, is calculated as a root mean square total of the weighted accelerations. Driving a bus at higher speeds increases the raw frequency and the magnitude of the vehicle's suspension impacts. These high-speed suspension impacts map directly into the 0.5 to 80 Hz frequency band. Operating in this high-frequency band causes the root mean square values to spike, exceeding ISO limits for physical human comfort. The equation for motion sickness, however, is the motion sickness dose value, or MSDVZ. While physical discomfort evaluates the instantaneous magnitude of high-frequency forces, motion sickness is an integral equation that measures low-frequency exposure integrated over time. A floating bridge's primary environmental excitations, ocean waves and wind gusts, operate directly in the ultra-low 0.1 to 0.5 Hz frequency band. If a bus driver intentionally reduces speed to mitigate the high-frequency suspension jarring, calculated in the RMS total, the equation shifts. Decreasing vehicle speed strictly increases variable t, the total traversal time spent on the bridge. Increasing t while the human body is exposed to that ultra-low structural sway maximizes the MSDVZ integral, significantly raising the statistical probability of motion sickness. The engineering solution is a narrow optimization window, a highly specific speed that balances the two competing metrics. This optimal speed changes based on the passenger's seating distance from the bus's center of gravity. By coupling classical free body diagrams with ISO frequency integration, engineers define the exact velocity rules required to safely transport human beings across moving structures tethered to the sea.